We've been working with functions with multiple independent variables. We know how to find the derivatives of these functions. So this section, we're going to talk about how to find the integrals. Section 5.1, we're going to start off with the simplest case, finding integrals over rectangular regions. And if we talk about a function with two independent variables, we will need to integrate twice. So let's get started and see how that looks. In Calc 1, when you learned how to find an integral, the first thing you talked about was that an integral can be used to find area under a curve. So maybe you have the curve that I have on the screen on the bottom left. And if you were asked to find the area under the curve, you probably started off with rectangular partitions. So on your x-axis, you would partition between some values a and b over some interval a to b. And let's say that we partitioned into 4 rectangles. We would start by breaking up the interval from a to b into 4 sections. We would take one of the endpoints. So you might remember that there were multiple ways to do these Riemann sums. You could do the left endpoint, where you take the left endpoint of each interval partition and plug it into your function, or you could do a right endpoint, or you could do a midpoint. But either way, you would take those values and plug them into your function to find the corresponding points on your function. So here I'm showing you the right endpoint. So for each one of these partitions that we've created, I took the right endpoint, plugged it into my function to find out where that function is for that specific x value. Then we drew rectangles for those partitions, calculated the area of each rectangle. So if you remember, area was base times height. The base is the width of this partition, so we call that delta x most of the time. Make a nice delta. And then the height, that's actually the function evaluated at that right endpoint. So a lot of times we would do like x star telling you, go back and see what type of endpoint I'm using. And then we would add up all of these areas. Now, we're going to talk about that same kind of partition for a function with multiple independent variables. So in Calc 3, we are starting out with like an xy axes, but those are both independent variables. So the same way that we hacked up the x-axis in Calc 1, we need to hack up the entire xy plane for Calc 3 because our function has x and y as independent variables. So we'll chop up the x-axis, then we'll chop up the y-axis. So now we've partitioned our domain into a bunch of tiny squares. So in Calc 1, you partitioned your domain to get small segments. In Calc 3, you partition your domain to get squares. From here, we would then pick either a left endpoint, a right endpoint, or whatever edge you want for one of these partitions, plug it into your function the same way that we did in Calc 1. So let's pick a point within one of our partitions, and I'm going to pick the center point, plug that into our function, and that's going to give us this vertical distance. So let's take a look at the image I have here. We have the XY plane partitioned, just like I had shown you in the previous image. We picked a center point. I should change the color of my pen. We picked a center point for one of those little squares in the domain, plugged it into our function, and found where that lives on the surface. Okay, now let's make a connection here. In Calc 1, when we did these partitions, we were looking at areas because we had a length and a height or width. So we're looking at rectangles. In Calc 3, we actually have an area in the domain before we give it the third dimension, the height. So when it comes down to calculating the area under a surface, or the quantity under the surface, sorry, it's going to look a little bit different. So we have our tiny rectangle in the domain that already has an area, but then we're going to multiply that by a height. Area times height, that's 3 dimensions. We're actually calculating a volume here rather than an area. So now if at the minimum, when we're talking about a function with at least 2 independent variables, when we do these integrals, we're calculating a 3-dimensional quantity. So let's take a look at that as far as Riemann sums. On the left, we have Calc 1. On the right, we have Calc 3. Notice the small differences, but also the similarities. So in Calc 1, we use these rectangular partitions to find area. In Calc 3, we're using a rectangular partition to create prisms to calculate a volume. We added up all of the rectangles in Calc 3 to create an approximate for the area, and each rectangle had some base times height. In Calc 3, though, we're partitioning over 2 separate independent variables, so we're going to sum over each one of those partitions. Each one of those partitions has area of a base times height, so we are looking at volume rather than area as our total quantity. And then we go down to generalize some of the notation. I don't want to spend a lot of time on it here because, in fact, this semester we don't have time to cover the nitty-gritty details. We have to just get the big picture here. Let's do a simple example to help illustrate what's going on here. So we're looking at a function with independent variables, x and y. The function is 3x squared minus y. And we're going to consider integrating over the region R, which is defined by this Cartesian product. The x values range from 0 to 2. The y values also range from 0 to 2. So the very first thing we're going to do is set up a double integral for finding the value of this signed volume. And I'll show you that this is saying integrate twice over R. We're integrating twice because we have x and y independent variables. We're integrating underneath the function 3x squared minus y, and we're integrating over some area partitions. And the way that this will look as a Riemann sum setup is going to be our limit. Well, before I tell you that part, I guess we'll have to draw a picture. So the rectangular region R that we're integrating over, the x values go from 0 to 2, the y values also go from 0 to 2. And if we were to partition this, let's think of a really simple partition. We are going to name each region or each point in our region by some index. So over the x values, maybe we index with I. So when we make our partition with x, we're indexing over I, so I can be 1 or 2. And then for y, we can index over a different letter. Let's use j. So j would go from 1 to 2 as well. So we have x sub I, x, and then y sub j, which means we're going to have to do a double sum. If I wanted to sum over all of the x values and all of the y values, I'm going to have to pick some point to use as my point to evaluate each one of these tiny squares. So I'm picking the top right corner in this picture to represent the points that I want to use to evaluate these squares. And I'm going to call each one of these squares some tiny region. So let's call each one of them R. I'm going to say this is R with x1 and y1. This is R with x2 and y1. This is R with x1 and y2. And this is R with x2 and y2. So I'm denoting each one of these regions with an R and subscripts to tell you where I am within this region. And then I can start to talk about the sums that we're going to integrate over. Each one of these points that I've got drawn up here, they are representing some pair of points like x and y, but they're special points that are tied to the I and j indices. So I'm going to say that it's x star with the subscript I, j, and this is also y star with that same subscript I, j. So each one of these points is corresponding to one of these special notations. We're going to plug those into our function, so we'll have f of x star ij, y star ij, and that's going to give us our height above each one of those regions. The area of each one of these regions is going to be similar or exactly the same because we've partitioned it evenly in both directions and our region is symmetric. So our area, I'm just going to call that delta A. So just like in Calc 1, we're going to approximate this double integral using Riemann sums. The calculation for each sum is going to come from evaluating our function at this point x star y star. If we plug that into the definition of our function, we get 3 times x star ij squared minus y star ij. And we don't need parentheses on that y one. So to calculate the volume, we're going to use that function evaluated at the special point multiplied by that area partition that we found from our region. And these are going to sum over all of the i's and j's, so we're going to need two sums, one to tell us where to go over the j values, and let's just say j can go all the way up to n. That's the maximum number of partitions in that direction. And then we have the I values. Those are going to go up to their maximum value of m. And in order for these two things to be exactly equal, I need to squeeze something in here. It's the limit, where n and m get to go to infinity. So without this limit, these are really only approximate, the double integral and the double sum. But if we let the limit of n and m go to infinity, then they're exactly the same. All right, so now that we have part A done, which is to set up the double integral for finding this, now we can move on to part B. Part B says divide r into 4 squares with m and n equal to 2. We already did that. You're welcome. We're going to choose a sample point as the upper right corner of each square to approximate the signed volume. We did that as well, but this time let's go through and find the exact values of those points. So instead of just saying generic x star, y star, let's go ahead and find the coordinates of those top right corners in our partition. So this point here, that has an x value of 2 and a y value of 1. This inside point over here is going to have an x value of 1, a y value of 1. Top right corner is 2, 2, and then this top center point is at x equals 1, y equals 2. So we have our 4 points there. Those are all of the x star, y star combos. Now that we have those, we're able to plug them into our function. So we're going to plug each one of those points into our function. So f at 1, 1 is going to look like 2. You can evaluate your function on your own. I'm just going to give you the numbers here. F at 1, 2 is going to look like 1. f at 2, 1 is going to look like 11, and then f at 2, 2 is going to look like 10. And then each one of these is actually multiplied by our area. So when we do this volume approximation, we're going to take each one of these values that we just calculated and multiply by the area of our partition. So if we think about what delta A is, like in this picture, it's a box that has side length 1, side length 1. So that area is equal to 1. So our volume is going to be F at 1, 1 times delta A, which is 2 times 1, plus F at 1, 2 times delta A, so 1 times 1, plus F at 2, 1 times delta A, which is 11 times 1, and then F at 2, 2 times delta A. And then we add all of those up, so we get 2 plus 1 plus 11 plus 10 for our final answer of 24 cubic units. So our volume is approximately 24 cubic units. And we know that partitions get better and better when we let M and N get larger and larger. So partitioning with only 4 rectangles, it's a pretty bad approximation, but I'm hoping that it gives you an idea of how we're using the rectangles and partitions for these functions of multiple independent variable. Part C would have us divide into 4 squares just the same way that we did for Part B, but this time we would pick the midpoint of each square to approximate the volume. So the only thing that's going to change is the points that we use to plug into our function. So each one of these values would be different. Delta A would be the same. I'll let you try that one on your own.